today we've got until 12:15, so my plan each week is perhaps to try and split the session into two bits with a quick 10-15 minutes in the middle, but we must be careful we don't waste any time because things could be quite tight. Today we're going to have a bit of a whistle-stop tour of Ohm's Law, power, this is not writing where I put the pen, series parallel resistance, Kirchhoff's laws. Yeah, so all of those would have been talked about in science back in year one. Remember that? That was with me, I believe. Okay, so we're going to have a bit of a whistle-stop tour for about an hour, going over those, looking at some problems, trying to make sure, remind you of what each of those are and the ways that we can calculate those. And then we're going to move on and have a look at something about the ideal voltage source and how we model a real one, an ideal current source, and how we model a real one of those. Okay, that leads into a number of circuit analysis techniques, one of which is called superposition. Yeah, so it's a method of analysing some more complex circuit networks, particularly ones with more than one source of voltage or current in them. Yeah, so it's quite a lot for one day. We'll see how much of that we can get through. Let's pause this. Moving on then. We've got Ohm's Law. Ohm's Law, basic relationship between the applied voltage, which we call, and well, as consistently as possible, an applied voltage is E for EMF. They're applying a force, and then when we talk about a volt drop across a component in a circuit, we'll call that a voltage V. Okay, but I'm going to try as much as possible to be consistent here. Remind me if I'm not, but textbooks will vary between calling it V and calling it E, sometimes even U, because the Germans use U to represent a voltage source, okay, and the current I. Ohm's law is the relationship between those three, okay, and it goes right through electrical principles. It always applies. Formula is, Andrew, yeah, R is equal to V divided by I. I actually like to think of it as the current version because the current depends on the other two. It's really the dependent variable on what voltage you apply and what the resistance of the circuit is. So changing that around, I is V over R. There will be no triangles at level 5, right? You can use them if you want to remember it, but I won't be putting them on the board. So that's Ohm's law, and it applies to any circuit. What we have to be a little bit careful of at this level is its application, as always, at an instant in time. We're going to be talking quite a lot about circuits that are always changing or transient, AC circuits and or DC circuits that switch on where there's capacitors and inductors involved and we've got a transient happening. But all of these laws apply at an instant in time. You can apply them at an instant in time. Okay? Are you all happy with that? Power. Power is about what's dissipated in a load when a current flows through it. And we apply some kind of voltage to that load. Well spotted. Deliberate mistake. A source E. Yeah, so that could be a battery, generator, could be any kind of source. 3 different ways of calculating power. Joe, give me one of them. P equals. There's one with I and R in it. Got to do something else to that. I squared R. Yeah. So that's one way to calculate it. The current squared times the resistance. Daniel, we got another one? Warren? Joe? Andrew? Yeah, we've done all 3 ways of calculating power, yes. There's a version involving V and R, and there's a version involving I and V. P, yeah, it's I times V, yeah. And the third one is V squared divided by R. And it's best if you are aware and know and are able to remember all 3, because then within the 4 values we got here, power, current and resistance and voltage, you can always, if you don't know, if you're given any 2 of them, you can find the power. So if you're given any 2 of E, I and R, you can find the power. So that means you can possibly avoid using a calculated value to find power. You can use a different formula instead. Okay? So that's about calculating power. Pretty basic stuff. Everyone okay with that now? Yeah? Also, we need to consider carefully when we're calculating values with multiples. We'll need to use for mega 10 to the power 6, kilo 10 to the 3, milli 10 to the minus 3, micro 10 to the minus 6, nano 10 to the minus 9, and pico 10 to the minus 12. And those last 2 there, always remember which way round they are, but remembering that they're in alphabetical order. Alright? So you're going to come across nano and pico possibly in values of capacitance mainly, milli in resistance possibly, current for sure, and also inductance in millihenries. Mega, you're only really going to come across that in resistance, maybe in watts as well. Kilo, you could come across that in most of the values other than capacitance or inductance. Okay, but if you use the powers of 10 values in your formulas, you don't have to worry then about the current being in milliamps and the voltage being in volts and so on, because that'll all work out in the end. Okay, so you need to be, and I'm sure you are, familiar with using the indices to do multiples and submultiples. Series resistance. Daniel, how do we calculate 3 resistors in series, RT? that's 10 ohms, that's 20 ohms, and that's 30 ohms. What's the total? So it is 60, so therefore what are we doing? Add them all up. Yeah, if you think about the current trying to flow through there, if I just got to go through 10 ohms of resistance, more would flow than if I also got to flow through 20 and 30 together. So adding them in series makes them bigger. It's R1 plus R2 plus R3, and that means we can carry it on for n number of resistors. Yeah? So series resistance, just add them up. For parallel resistance, we have 3 different methods depending on what we've got. First of all, a method when all these are perhaps different values, 16, 20 and 40 for instance. So where we've got more than 2, and they are, in fact this method works regardless of what the values are, but when you've got values that are the same or you just got 2, there are alternative methods. Anyone remember how we do this method of calculating total resistance in parallel? Yeah, RT, the total, and we have to have some brackets here, right, because you're almost there. It's R1 to the minus 1, that is 1 over, yeah, plus R2 to the minus 1, plus R3 to the minus 1. We can carry that on to Rn to the minus 1, but we have to take the reciprocal of the result of adding all them together. Right? What you were saying is 1 over R1 is equal to 1 over R2 plus 1 over R3 plus 1 over Rn. Yep. But what students tend to do with that is they forget that it's 1 over R1 RT is equal to that, and they forget sometimes to take the reciprocal of the result to turn it into RT equals. So the way that should really be written is RT is equal to 1 over all of that. That there is exactly the same as that, because to the power minus 1 means the reciprocal of. Okay? And the way I tend to do that with my calculator is I put 16 to the minus 1 plus 20 to the minus 1 plus 40 to the minus 1, press the equal sign and get an answer, and then do the reciprocal on that answer afterwards. That's rather than mess around with brackets. That's just my method. Okay? So, second possible way we can have is if we've got any 2 different values. Anyone remember the method there? And you can actually give it a name. It's called product over sum. Yeah. So RT in this case is equal to the product. What's the product? What do we mean when we say the product of 2 numbers? What's the sum of 2 numbers? Yeah. So it's R1, the product and the sum is R1 plus R2. The product must be something different, and it's actually R1 times R2. And we will, in my notes, use dot notation for multiplication with algebra, right? But when you put the numbers in, gents, you put the multiplication sign. When you got algebra representing values, we use the dot notation. So that you can use that consistently for two resistors together in parallel. Okay. Thirdly, there's a quick get out when you have multiples of values that are exactly the same. So in this network, we've got three resistors and they're all of the same value R. If you get that kind of situation, for instance, they're all 30, think about what's going on here, right? We've got a current flowing here, I, and it's split into three currents, 1, 2 and 3, there, and those three paths are all equal. So the overall resistance to that current must be a third of what it was if we only had one resistor there. It's got three different directions of equal ease to travel through. So RT, in this case, is equal to the value R divided by N, where N is the number of resistors. So if we put 200s in parallel, we get 50 ohms. If we put 400s in parallel, we get 25, and so on. So the second two are quicker ones where we get multiples of all the same value, or we got just two. Okay. The first one will always work with any parallel network, but just try and spot where one of these two quicker formulas will get you the answer in one go. Okay. Everyone reasonably happy with that? And then we get two different types of combination circuit. This is where we've got a resistor in one single resistor in series with three others in parallel. Yeah. To calculate the total here, we would do the parallel. I asked you. I've given it away now, really, haven't I? Right, the first thing we do, we're trying to turn it into, we haven't got a formula that combines this series and parallel network, but we're trying to turn it into either all series or all parallel, and then we can find the overall answer. So the first thing we do is calculate that bit. We find R2, 3, 4 using the whichever formula is appropriate. R1, R2 to the minus 1, R3 to the minus 1, R4 to the minus 1, all the minus 1. We do that, and then RT is R1 plus R2, 3, 4. Do you remember doing some stuff like that? Yeah? And actually I've got a pack of revision notes for you that is basically pulled from the science with some self-assessment questions for you to go through that might look a little bit familiar, but it's worthwhile over the next week having that practice. Yeah, to refresh this particularly bits that you don't necessarily know that well. Okay, so that's one type of combination where we've got a resistor and a single one in series with another one in parallel. Now this bit could be another parallel network, so we've got two parallel networks in series with each other. So you calculate the two parallel networks separately and then add the results together. So it can get more complex, and there's some examples like that in the notes that I'm going to give, the revision notes that I'm going to give you. The second type of combination is where we've got two series networks in parallel with each other. So the trick here is to calculate the total of those two. R12 is equal to R1 plus R2. Calculate the total of these two. R3, 4 is equal to R3 plus R4. Yeah. And then RT is the two results added together. R12 plus R34. It's a matter of looking at that network and finding out how we can break it down into how we can join two resistors together some way, either using the series or the parallel method, to simplify that network bit by bit. And some of the ones in the notes I've done for you are more complex than that, so you've got to look at how you can break it down, gradually work it towards combining two resistors in one. What you're doing is, here you're saying, what resistor could I put in there instead of those two and still having the same circuit? And you're doing the same down here. And then overall you're saying, what value of resistor could I put in there to replace all of that with just one resistor? That's what it is, calculating the total resistance. So, moving on a little bit further then, as to what happens in these circuits when we add a voltage source. We'll change that to ES. We connect two loads in parallel, or two resistors in parallel to a voltage source. In a parallel circuit, in a series circuit, there's only one current. The same current flows in every part of this circuit. So if I put an ammeter in here, here, or here, I would measure exactly the same current, because everything that leaves that terminal and this arrow here always points towards the positive terminal on a source, right? And it's always points in the direction of conventional current. We must get used to putting arrows for voltages on the right way round if we're going to get our Kirchhoff's law stuff correctly. Okay? Current flows, the same current, all the current that leaves this positive terminal ends up back there by some route or another. We don't lose any current anywhere. We do, however, when current flows through a resistance, we get a voltage difference across that, or a voltage drop. Those arrows go in the opposite direction to the current flowing through that load. Again, that's important with regard to Kirchhoff's laws. So a parallel circuit is a voltage divider. Kirchhoff's law says that these two will add up to that one. So that's 10 volts, and these are two 10 ohm resistors. We'll divide that voltage in half. We'll get 5 volts there and 5 volts there. Alright, series circuit, current's the same, voltages across the components is different. Why have I got that twice? God knows. In a parallel circuit, conversely, we have the source here, ES. I'll give it a direction that way, so that's the positive terminal. The total current flowing away from it, but it splits, so you get a current divider for a parallel circuit. The volt drop across both these two is actually the same, because this point and that point are connected to the same place, and so are that point and that point. So the voltage drop for both of those two is actually the same value, and it's equal to what we're applying in this case. Right? These two currents add up to IT. That's Kirchhoff's current law. We don't lose any. Alright? Everything that goes into that terminal goes out of it somewhere, and it joins back together again here to become IT again. So these two currents there and there are the same. I put an ammeter in those two places, get the same value. But if I put ammeters here and here, they'll be different. If these two values are the same value, those two currents will be equal and half of that. It all makes sense, really, once you get used to it. And it applies in any circuit, any moment in time. Doesn't matter if things are changing. Yes, it's changing, but all those laws and rules will stand true. Kirchhoff's law will always stand true. Now, what you need, and I find where students come unstuck with this type of analysis in particular, is when we start to get a combination. Yep. We start to label that up. We've got a voltage arrow there representing the source. Okay. A total current IT will flow there. So IT is flowing through that resistor, R1. We get a volt drop V1 across it. Then the current IT splits here into I2, we'll call that if that's going through R2, and I3 that's going through R3. And then the whole lot of current joins up again and becomes IT the other side. These voltage arrows, remember, have to oppose the current flowing through the component. So we get a voltage arrow here, V2, and that's actually the same V2 across there. But time and time again, I see students trying to calculate these two currents using the total voltage for some unknown reason. And you can't do that. Yes, there's a parallel circuit. When you've got just a parallel circuit, it is the supply voltage that's across each resistor. But in this circuit, we're going to lose some voltage across R1 before we even get to this one. These two, V1 and V2, would add up to that total. So we're going to lose some there. If this is 20 volts, and that's 6 volts, what you've got across here is the remainder 14. But time and time again, I see students calculating these two currents using the total 20 volts for some unknown reason. So just be careful of that. Okay? And we're going to use that a heck of a lot during what we're learning with the network theorems and such like. I just wanted to do a whistle-stop tour of it just to remind you of it. We've got plenty of chance to practice those skills anyway, and I'm going to give you some notes in a minute that will help you to revise that a bit more over the coming week. And I do recommend that you do some practice.